Okay, everyone, so here's another SI session. This one is to make up for Monday, March 1st session, which I had to cancel due to not feeling very well. Okay, so tonight's focus is going to be on chapter 14, which is acid-base equilibria. Now, we started this back around February 24th and 22nd, I believe. That week we started to go over this chapter. However, because of your exam, we kind of diverted away from it. Right, so today was your exam on chapters 12 and 13. So hopefully those went well. So what are we going to cover? What's kind of SI going to look like? Well, today I just want to touch upon two short topics from chapter 14. Okay, they're not very long, but they're both very important topics. Okay, so the first thing that we're going to go over is the 5% rule. The second thing we're going to cover is polyprotic acids, which are just acids that have more than one proton, right? The term polyprotic means multiple protons. So we'll go over those topics tonight, and then in Monday's session, we will do a chapter 14 review, right? I know we've kind of gone over chapter 14 over several SIs, some of which seem to date back a pretty long time ago at this point. So we'll start the beginning of Monday's SI after going through the challenge problems. We'll go and kind of briefly touch upon all the topics from chapter 14 that we've already covered during SI. Okay, and then the remainder of Monday's session, we're going to do a chapter 14 wrap up, right? So when I've taught chapter 14 in previous SIs, this year's lectures hadn't been released yet, and so I based what I taught based on previous year's lectures. And so part of the wrap up is I'll look at what was covered specifically this year and just make sure I touch upon any topics that we haven't previously touched upon. Okay, so basically Monday we're going to kind of touch upon every topic in chapter 14, but we're going to have a greater emphasis and a greater focus on the topics that we haven't yet covered in SI. Okay, and one of the things I'm going to try to do for Monday's session is I'm going to try to list out the topics from chapter 14, and I'm going to, next to each topic, I'm going to indicate when I went over that in SI, but I'm also going to indicate where your professor goes over it in lecture, right? Because I think you have maybe 5 or 6 videos for chapter 14. And so I'm just going to indicate where you can find every topic, whether you want to find it through my SI videos or through your lecture videos. Okay, so that'll be Monday. Next Wednesday, we're going to actually skip ahead to chapter 15, right? So Monday we'll pretty much finish chapter 14 up. So Wednesday we'll go on to chapter 15, where we'll be covering titrations. Okay, just a forewarning, when we get to titration problems, they often take a really long time to do and to go over. And so just be wary of the fact that when I give challenge problems for buffers and titrations, just realize that you're going to be getting many fewer questions than you're used to, right? So on Wednesday's session, March 10th, I'll probably only give you one challenge problem that night. And the reason for that is it'll be a titration question with probably 4 different parts, okay? And so it's just a very lengthy question, and so there's just not enough time in a session to go over, 4 titration problems and then move on to the next material. Okay, so just kind of be advised that when we get into longer problems like titration problems, just the number of challenge problems are likely to decrease. Okay, then looking ahead to the next week, so Monday, March 15th, we'll move on in chapter 15 to buffers. Okay, so same thing, buffers, these problems take a fair amount of time. And so the challenge problems associated with this session, you'll probably only get 2 to 4 problems, right? You'll definitely get more buffer problems than titration questions just because of the length of time it takes to solve them. But just realize that it will be a decreased number of questions for each of those. Okay, and then looking ahead to that Wednesday, right? This is the final session before a multiple choice exam. And so we'll kind of get away from chapter 15 and we'll come back and look at chapter 13, which is equilibrium, and chapter 14, which is acid-base equilibrium. Okay. And then again, Friday, you're going to have an exam. Okay, so that's kind of just looking ahead, trying to figure out what our schedule is going to be for the next couple weeks. So really, before I jump into the two topics that we're going to discuss today, I just kind of wanted to look at how I write acid-base equilibria. Okay, so at first, we're just going to look at these top two, which shows the dissociation of hydrofluoric acid, or HF. Now, something I want to just make sure that you're aware of is these two equations are exactly the same, right? They mean the exact same thing, right? If you start with HF in the aqueous, right? So you have aqueous hydrofluoric acid, it will dissociate into its ions, an H+ ion and an F- ion, okay? But you can also write it as your HF, because it's aqueous, it'll be in water, right? So HF aqueous means it's in water, so HF plus liquid water. And the reason why we sometimes write it in this way, right, HF plus water, is now we have two chemical species on our reactant side. We very clearly have HF, which is an acid, and now we have water, right? And if HF is our acid, that means water must be our base, right? So HF as the acid is going to lose a proton, water as the base is going to accept it, and when that happens, we're going to form hydronium, which is H3O+, and F-. Okay, so just note that H+ and H3O+ are the exact same thing. Okay, they're completely interchangeable. Okay, and so this is two ways to write the same exact reaction where you start with a weak acid and it dissociates into its ions. Again, they are equally correct. Okay, now let's move on to a weak base. So a classic weak base would be ammonia, NH3 aqueous. So if I tried to write my equilibrium for ammonia, like I did hydrofluoric acid, right? If I just write NH3 aqueous goes to, well, NH3 is not reacting with anything here. And so it's kind of hard to interpret what the products would be. Okay, so when we work with weak bases, right, you're always going to start with your weak base and you will always react it with liquid water. Okay, so in this case, ammonia is a weak base. Because ammonia is a base, that means water has to be acting as our acid here. Okay, and so water will lose a proton, ammonia will gain that proton, which will form ammonium, NH4+, and a hydroxide ion. Okay, so as you can see by looking at the base, these two base equations, right, you can't really write an equation starting with a weak base unless you react it with water, right? And so just for your reference, right, looking back at HF, you can write it either of these two ways, but personally, I will always write it this second way during SI, because in terms of format, it's just exactly the same as how I'd write an equation starting with a weak base. Okay, so you can write this first equation up here, but again, in terms of style, I'm going to stick with the ones that have stars next to it. But yeah, just in case that's something you're wondering about, why do I react HF with water instead of just writing HF goes to its ions? That's the reason why one equation isn't more right than the other. It's just a style preference. Okay, moving on to actual new material. So what is the 5% rule? Okay, so we have recently learned about ice table problems, right? In a classic ice table problem, they will give you an initial concentration of weak acid or weak base, right? They'll give you that initial concentration, and they'll also give you your equilibrium constant K. What this causes you to have to do is write out your ice table with your change in terms of X, and then you'll get equilibrium concentrations of reactants and products in terms of X. Okay, and what you need to do from there is use the quadratic formula to solve for the value of X. Okay, and the quadratic formula, if you're not familiar with it, is this equation up in the top corner, where A is the coefficient in front of X squared, B is the coefficient in front of X, and C is the term with no X associated with it. Okay, now the problem with the quadratic formula is that it can be very time consuming to plug it in, because you have to plug it in twice, and it can also be error prone, right? Especially in previous years where we weren't allowed to use graphing calculators, many people would get these problems wrong by accidentally plugging in the wrong values into the quadratic equation. Okay, now that you can use graphing calculators, based on how the semester is set up, that is a little easier to avoid. But all in all, using the quadratic formula to solve for the value of X can just lead to errors. And so because of that, we use what's called the 5% rule, right? And this 5% rule is really just to make your calculations easier. Okay, and so you have to make a really big, or you have to make an assumption when using the 5% rule. And this assumption is that X is really small compared to our initial concentration of acid or base. Okay, and so if X is really small compared to that initial concentration, then it won't really affect the initial concentration, right? And so if we ignore it, it's not really a big deal. Okay, that's kind of the assumption we're making, that if we ignore X, it's not really going to affect our answer because it's so small compared to our initial amount. Okay, and so based on this assumption, we're going to ignore X whenever a term is A plus X or A minus X, right? And A could just, that typically is your initial concentration, right? So A would be some numerical value. Okay, and so whenever you see A plus X or A minus X, whenever you use the 5% rule, you're just going to pretend that plus or minus X does not exist. Okay, and so if you had A plus X or A minus X, you're going to ignore the X, and it's just going to become whatever that initial value was, right? Whatever A represents. Now, an important thing to note is that you only ignore X when it comes up in this context, A plus X or A minus X, right? If the concentration of a product or reactant at equilibrium is just equal to X, you cannot ignore it, okay? And that might become more evident. I have an example on the next two slides. Okay, but if at equilibrium the concentration is equal to just X, you cannot ignore that. Okay, and then lastly, you're going to just solve for X. And once you solve for X, you have to actually check your work. Okay, and so what you're going to do is you're going to take the value of X and you're going to divide it by that initial concentration of acid or base and multiply it by 100. Right? Multiplying it by 100 just turns it from a decimal to a percentage. Okay, and based on this, one of two things will occur. If the percentage is less than 5%, that means that the assumption that X is really small compared to our initial concentration, if our percentage is less than 5%, that assumption is valid, and that means that the value of X that you solve for is correct, and you can continue on with the problem. The other scenario, however, is if you do this check and it comes out to greater than 5%, that means that your assumption is not valid. Basically meaning X is actually big enough where it does affect our initial concentration. Therefore, we can't ignore it. Okay, so if you ever do this check and it comes out to greater than 5%, you actually need to go back and solve for X using the quadratic formula or quadratic equation, right? You can't ignore X if it's greater than 5%. Okay, sorry about that. I actually had to just stop the recording for a second because I was coughing. But now let's look at an example, because I think it's a lot easier to interpret the 5% rule when you're actually looking at like a numerical example. Okay, so a beaker contains 1.7 normal hydrofluoric acid, and the KB is given. Given this information, what is the pH of the solution, right? So it's a very straightforward question. So starting at the top, right, I just write HF, and I am given a KB. Now, hydrofluoric acid is an acid, which means we don't care about the KB, we're gonna care about the Ka. Okay, and definitely note this because the professors love to do this on exams, right? If you need the Ka, like we do in this problem, they'll often give you the Kb. If you have a base and you need the Kb, they will often give you the Ka. Okay, so just be very careful about that because you don't want to make an early mistake that'll affect the entire problem. Okay, and so in order to solve for Ka, we need to know this extremely important relationship that Ka times Kb will always equal 1 times 10 to the negative 14th. Well, knowing the value of Kb, we can use this relationship to find that the Ka would, for hydrofluoric acid would be 6.6 times 10 to the negative 4th. Okay. Now that we have that value, I want to find the molarity of my HF solution, right? Because we were told that it's a 1.7 normal solution of HF. Well, what does that mean? If you have a 1.7 normal solution of HF, that really means that you have 1.7 moles of H plus per 1 liter of solution. And then we can use our stoichiometric ratio to know that 1 mole of H plus is equivalent to 1 mole of HF. Therefore, in this circumstance, we actually have a 1.7 molar HF or hydrofluoric acid solution. Okay. Now, if this was a diprotic or triprotic acid, our normality and molarity would not be the same, right? Because di and triprotic acids, we have multiple protons per 1 mole of acid. Okay, but for a monoprotic acid like HF, the normality and molarity will always actually be the same. Okay, now that we know the molarity or our starting amount of weak acid, let's create an ice table, right? So I'm just going to write my balanced chemical equation, right? So I'm going to react hydrofluoric acid with water to produce hydronium and F minus. Okay, and I'm going to write ice down the side. I stands for initial, so our initial concentration, right? So we just figured out that our initial concentration of HF is 1.7 molar. Okay, you might notice I drew a line under water, and that's because water's in the liquid phase, so we're not really going to even look at it in ice tables. And for the initial amounts, just notice that unless they tell you otherwise, you assume that you have 0 product to start out with. Okay, next we're going to look at our change. Well, we don't know what our change is, and so we're just going to put it in terms of X, right? So for our reactants, we're going to write minus X. For our products, plus X, right? And all the coefficients in our balanced equation are 1, and so it's just going to be plus or minus 1x, depending on if it's a reactant or a product. Lastly, for the row beginning with E, E stands for equilibrium concentration. We're just going to write it in terms of X, so 1.7 minus X for HF. And for both of our products at equilibrium, their concentration will be equal to X. Okay, and so our Ka, or our acid dissociation constant, will be equal to the concentration of hydronium times the concentration of fluorine divided by the concentration of reactant, which is hydrofluoric acid. So what I do here is I plug in my value for Ka that we found above, and this is going to be equal to the concentration of our products, which was X times X, which is X squared, divided by our concentration of HF, 1.7 minus X. right? Notice that I'm plugging in my equilibrium concentrations here. Now, if I wanted to, from this step, solve this out and use the quadratic formula to get the correct answer, or to get the answer, that would be perfectly fine. And if you use the quadratic formula, you will get the correct answer every single time, assuming you plug it in correctly. Okay, but again, it is much harder. And so many people, like myself, like to use the 5% rule. And so what we're going to do is we're going to ignore x. Okay, and by that, realize that we didn't ignore any x's in the numerator, right? We only ignore the x in the denominator where we have some value minus x, right? Because it's some value minus x, we can ignore this x, and we're going to rewrite our Ka expression as Ka, or 6.6 times 10 to the negative fourth, is equal to x squared divided by 1.7. Okay, and because of this expression, it's much simplified. We can very quickly solve for x, and we find that the value of x is 0.0335. Okay, and so again, that is our value for x. But whenever you use the 5% rule, you must check to make sure that's a valid assumption. So as you can see, here's my little check on the side. So in the numerator, I'm going to plug in that value of x, so 0.0335. And the denominator, I'm going to plug in my initial concentration of HF, which is that 1.7 value. Okay, and then I multiply it by 100 to turn it into a percentage. And when I find it, I find that it's only about 1.97%, meaning that x is really small compared to our starting amount of HF, and that my assumption of ignoring x, that was valid, right? This value of x that I calculated is the correct value, and I can continue on with my problem. Okay, so now that we know for sure that x equals 0.0335, right, I need to recognize the fact that x, this value, is equal to my equilibrium concentration of hydronium, which is the same as H+. So the answer to the question of what is the pH, right, pH is equal to the negative log of my hydronium concentration. Well, now that I know my equilibrium hydronium concentration is this x value, I can plug that in and find that my pH is slightly under 1.5. Okay, and so again, just to summarize, if you prefer to use the quadratic formula to solve for x, you will get the correct answer every time. If you like the 5% rule because it's much easier, it does work for most problems, but you do need to check, because if it's greater than 5%, you have to go back and solve it using the quadratic formula, or you will get a slightly incorrect answer. Okay, moving on to the second topic for this evening, it's polyprotic acids. So again, these are acids that have multiple protons. Okay, and so the most common type of polyprotic acid we'll look at is diprotic acids. Okay, the prefix di meaning two. Okay, so diprotic acids just have two protons. So examples of this would be sulfuric acid, carbonic acid. Those are honestly the only two coming to my head right away, right? But those are the two most common ones you will see. Especially in this course, you will see carbonic acid problems a lot, right? H2CO3. And the thing to note about diprotic acids is that they have two separate equilibriums, right? In the first, it'll be for the dissociation of the first proton, and the second equilibrium will show the dissociation of the second proton, right? So I listed the two equilibriums that we see for carbonic acid. So our first equilibrium is carbonic acid, and it's going to partially dissociate into H plus and bicarbonate, right? HCO3 minus is known as bicarbonate. You could also call it hydrogen carbonate, but you typically hear bicarbonate, and that's more, you use that term a lot more in biology. This is actually a buffer present in your blood, which is why you'll hear it. That helps you maintain pH balance. But this, in case I say bicarbonate and you're not too familiar with that, that's what HCO3 minus is. Okay, and so this equilibrium right here has its an equilibrium constant, right? K1, and this is the value. Now, we actually also have a second equilibrium, which is for the dissociation of that second proton. Okay, and so now we're going to start with bicarbonate, right? And bicarbonate can dissociate into H plus and carbonate, right? So it can lose its proton. And so this has its own unique equilibrium constant, which is listed here. There's also things called triprotic acids that have 3 protons, and these would have 3 separate equilibriums, just like we see for carbonic acid. Okay, and so the most known triprotic acid, especially in this course, would be phosphoric acid. Okay, and at some point during SI, I will probably bring a problem that involves phosphoric acid, right? A triprotic acid. However, on exams, your professors tend to ask about diprotic acids. Okay, that's a very, very common type of question to see. Triprotic acids, I'm not sure if I've seen one up to this point on an exam. However, you definitely have the ability to solve these problems, right? It's just using these basic ice table principles. And so what's a typical polyprotic acid question? Well, again, they typically will give you a diprotic acid, and they'll give you an initial concentration along with the equilibrium constants, right? So they give you K1 and K2 along with an initial concentration. And they typically ask for 2 things, right? So if it's a long answer, they'll ask for both of these. If it's a multiple choice question, it'll actually be 2 different questions with the same given information, right? So the prompt will be the same. One of them will just ask you, what's the pH of the resulting solution? And the second one will ask for the concentration of X2 minus, right? X2 minus is just a general term, and it's just standing for the conjugate base in this second equilibrium. Okay, and so for bicarbonate, or sorry, for carbonic acid, they'd be looking for the concentration of just the carbonate ion. Okay, so let's look at a classic example. So again, we're going to be looking at the carbonic acid example. So let's pretend we have an initial concentration equal to 2.5 molar. Okay, they give us the equilibrium constants, and they say, given these conditions, what is the pH of the solution and the concentration of carbonate at equilibrium? Okay, so again, these are the 2 things they most frequently ask for in a polyprotic acid problem. Okay, and so what we're going to do is you're always going to start with that first equilibrium, right? So we're going to focus first on our dissociation of carbonic acid into bicarbonate and hydronium, right? So I'm going to just write my equation. So I'm going to react bicarbonate with water, because that's, again, stylistically, that's how I always do it. And when we do that reaction, we'll get hydronium and bicarb. Now I'm going to write ice down the paper, and I'm going to insert my initial concentrations, right? So again, in this case, they don't tell us anything about our products and how much of that we start with. And so if they don't mention that, we're assuming 0. Okay, so we have no products to begin with and 2.5 molar of our acid. Now again, just like before, we're going to put our change in terms of X. So minus X from reactants plus X from products. And then we're going to write our equilibrium concentrations in terms of X, right? So 2.5 minus X for carbonic acid and X for each of our products. Okay, now I'm going to take my Ka1, right, which I just labeled as K1 previously, but the A just stands for the fact that this is an acid, right? So my Ka1 is going to be equal to my concentration of hydronium times my concentration of bicarbonate divided by my carbonic acid concentration. So again, I'm going to plug in all my values. But again, having 2.5 minus x makes it harder because I'd have to use the quadratic formula. So what I'm going to do is I'm going to ignore x and just write 2.5 in the denominator. This makes it much easier to solve for the value of x. I solve and find that x equals 0.00106. Okay? But this is a very, very important step. I made the assumption that the 5% rule is valid, and so I have to check that to confirm it. So my check, I'm going to take the value of x, so 0.00106, divide it by my initial concentration of acid, 2.5, multiply it by 100 to make it into a percentage, and I find that it's 0.042%, right? It's not even 1%. So my assumption was very, very valid that x is so small compared to my initial concentration of carbonic acid, which was 2.5 molar, that ignoring this minus x part is valid, right? And you can even see that doing 2.5 minus 0.00106 isn't gonna affect my value of 2.5, right? It doesn't change it. Okay, and so we solve for x based on our 5% rule. Our assumption was okay, and so x does indeed equal 0.00106, which is really our concentration of hydronium and bicarbonate. Now that we know these equilibrium values, we are going to turn our attention to the second equilibrium occurring. Okay, so as you can see at the top, I'm going to write out my second equilibrium. So now I'm going to react bicarbonate with water to produce hydronium and carbonate. And again, I'm going to write ice down the side. Now here, we actually have multiple initial concentrations, right? We can see in our equation that we have bicarbonate and hydronium, H3O+. And on the previous slide, right, let me just go back for a second, we said that the concentration of these is equal to x, which is 0.00106. And so that's how I know that the initial concentration of both bicarbonate and hydronium needs to be that, that value, that 0.00106. Okay, now we know nothing about how much carbonate, CO32 minus, we start with, and so we're going to assume that that is 0. Just like before, we're going to put our change in terms of x. So again, we're still going to do minus x for reactants plus x for products. And now I'm going to solve for my equilibrium concentrations in terms of x, right? So for bicarbonate, it's 0.00106 minus x. For hydronium at equilibrium, my concentration is 0.00106 plus x. And my concentration of just carbonate at equilibrium is equal to x. So now I write an expression for my Ka2, right, which I labeled as K2, right? This is going to be equal to the concentration of our products divided by the concentration of reactants in the aqueous phase, of course. So what I do from here is I plug in my values, right? So my Ka2 was at 4.7 times 10 to the negative 11th, right? I plug in my concentration of hydronium, I plug in my concentration of carbonate and bicarbonate, and what I do is I want to use the 5% rule again, so I'm going to ignore x. Well, remember, we ignore x anytime it's some number plus x or anytime it's some number minus x. Okay, and so we actually ignore two x's in this case. Do notice, however, that we are not ignoring this x that stands alone. It's only the x's that are added or subtracted from a number with an actual value. Okay, and so when we ignore both of these x's, it actually comes out that 4.7 times 10 to the negative 11th is equal to 0.00106 times x divided by 0.00106. Well, that value of 0.00106 in the numerator and denominator cancel each other out. And so we find that x actually equals 4.7 times 10 to the negative 11th, which was that value of Ka2. Okay? So now that we've solved for this value of x, again, we use the 5% rule, so we have to check to see if that was a valid assumption. So here's my check. Again, I'm going to put that value of x in the numerator, 4.7 times 10 to the negative 11th. I'm going to divide it by my initial concentration of my bicarb here, my bicarbonate, so 0.00106, and multiply it by 100 to turn it into a percentage. And as you can see, this is an absolute minuscule percentage, right? It's not even at all close to a single percent, never mind 5%. So this was a completely valid assumption. So now that we know x equals 4.7 times 10 to the negative 11th, we can look up at our ice table. And our equilibrium concentration of carbonate, CO3 2-, is equal to just that value, x. And so for the question, what is the concentration of carbonate at equilibrium? Your answer would be 4.7 times 10 to the negative 11th. Okay, and maybe write a little star next to this or something in your notes. I always encourage students to solve these problems out completely. However, if you ever come under if you're ever on an exam and you're running out of time and you have a diprotic acid question and they ask you for the concentration of carbonate or the concentration of whatever your conjugate base is in your second equilibrium, right? So carbonate is our conjugate base in our second equilibrium here. I don't think I have ever seen a problem where the concentration of that conjugate base is not equal to your Ka2. Okay? And so I, on an exam, encourage you to solve this out mathematically. But if you're ever running out of time, especially if it's on a multiple choice exam, and they ask you for the concentration of carbonate or the conjugate base of your second equilibrium, I don't think I have ever seen a problem where it does not equal your Ka2. And the reason for that is that your concentration of hydronium and that acid, I've always seen that they're the same value and cancel. Okay? And so that's just a little thing to keep in mind, and definitely kind of check that hypothesis as you do more and more of these problems. But in my 5 years around this course, again, I have not seen an exception to that. Just a little a trick to keep up your sleeve. Okay, so let's now focus on the second part, which asks for the pH of the solution. So let's remember that the pH is equal to the negative log of our hydroxide, of our, it's the negative log of our H plus or hydronium concentration, right? So negative log of H plus or H3O plus. Now, what is our concentration at equilibrium of our hydronium? Well, we can look up here. At equilibrium, our concentration of hydronium is 0.00106 plus x, where x equaled 4.7 times 10 to the negative 11th. Right, so this first portion, that 0.001 portion, came from our first equilibria. This second portion came from our second equilibria. Okay, and so I take the negative log of this entire thing, so I add these together, take the negative log, and I find the pH is 2.97. Now, another little trick to keep up your sleeve. This one works in most cases. However, I'm a little less sure that it works in every case. Okay, but in most cases, especially if your 5% rule works, right, by doing the 5% rule, we're saying we can ignore x because x is so small compared to the actual number here, right, that 0.001. So if your 5% rule actually works, well, let's look down here. We're taking this 0.001 number and adding to it x. But we already above justified that x is so small that we can just ignore it, right? And so all I want to show you here is if you just take the pH of the negative log of just this 0.001 number, basically you ignore x and take the pH of that, you just get the same value. Okay, now adding these two numbers together, taking the negative log of that is not a big deal, but just something to keep in mind as well, that if you do the 5% rule and x truly is very small compared to that number, well, when you calculate pH, you don't really need to factor in that second number if you've already, through the 5% rule, shown that it's insignificant compared to the magnitude of the previous number. Right, again, 4.7 times 10 to the negative 11th, that is minuscule, right? This is 1.06 times 10 to the negative third. They are about 1,000,000 times off of each other, maybe a billion or even trillion. I don't know. I can't do that math that quickly in my head. Okay, so that's all I have for you guys tonight. So on Monday's session, I will do a Q&A of the 5% rule and polyprotic acids. So please write down your questions while watching this and bring them because I'm happy to clear up any confusion. Okay, so I do have some challenge problems that we're going to go over on Monday from this material. It's just these two, and then I'll also go through the other challenge problems that we'll review on Monday. But these two, it's actually less of a challenge problem and more of an activity, right? I want you to go through these problems and solve it one time using the quadratic formula and the other time using the 5% rule. Okay, now number one should follow the 5% rule. So I want you to solve it through these two different methods to just prove that your answer will be exactly the same. Right, so if you want to ignore x, as long as it follows the 5% rule, you're going to get the answer right. I just kind of want to prove that to you. Now, the second one, this is one that does not follow the 5% rule, right? If you solve it out, you'll find x is too big. And so I want you to solve it out, still using the 5% rule, like use it, the 5% rule, and kind of pretend like it does work, okay? And then solve it out using the quadratic formula, and I kind of want you to be able to compare them and say, oh, you know what? When it is greater than 5%, my answer would come out differently, which is why I can only solve it using the quadratic formula. Okay, so this is more of an activity than a challenge problem, but I think it kind of shows why doing that check during the 5% rule is actually the most crucial portion of it. Because if you don't remember to check it and it's greater than 5%, you actually will get the incorrect answer. Okay, and then quickly, this is just another challenge problem. Just kind of fill it out using the given information. So each row corresponds to like together. So what's the pH of this solution type thing? Like when the pOH is 4.73, what's the pH? What's the H plus hydroxide? This is something we'll go over on Monday. And then lastly, these two, these are kind of your very classic chapter 14 questions. The first one, you're given a Ka, an initial amount, you're asked for pH. Number 5, you're almost working backwards where you're given a pH and a Ka, and they want you to kind of infer about how much you started with. Okay. That is all I have. So again, please feel free to email me or write down your questions and bring them Monday. If there's anything that is confusing to you, by the time this is uploaded, you probably will have taken your exam. And so hopefully that went well for everyone. And have a great weekend. See you guys Monday.